In the previous lecture, we discussed Avogadro's hypothesis and the Boltzmann constant. Now we're actually going to apply our findings and solve the following problem. The lowest pressure that is attainable using the best vacuum technique is about 1 × 10⁻12 newtons per meter squared. If the container has a temperature of 273 kelvins, determine the number of molecules inside our gas container, assuming the volume is 1 meter cubed. So we have the following container that has a volume of 1 meter cubed, and we use our vacuum technique to pump some of those molecules out. Eventually, we get to a pressure of 1 × 10⁻12 newtons per meter squared, and the volume remains at 1 meter cubed. So we want to determine the number of molecules of gas found inside this container. So let's begin with the ideal gas law. The ideal gas law states that the pressure times the volume is equal to the number of moles of gas multiplied by the universal gas constant R multiplied by the temperature given in kelvins. Now, recall from the previous lecture that N, the number of moles of gas, is equal to the total number of moles N divided by Avogadro's number Na. So if we take R and divide it by Na, we get the following ratio: R divided by Na multiplied by N multiplied by T. Now R and Na are both constants, and this ratio is commonly known as the Boltzmann constant, given by the letter K. So P times V is equal to K, Boltzmann constant, multiplied by N multiplied by T, where N is the number of molecules of gas found inside our container. So this is the thing that we want to calculate. So let's rearrange this equation and solve for N. The number of molecules N is equal to the ratio PV divided by K times T. Now we know what P is. It's given to be 1 × 10⁻12 newtons per meter squared. We know what V is. It's given to be 1 meter cubed. We know what the Boltzmann constant is. That's 1.38 × 10⁻23 joules per Kelvin. And we multiply that by our temperature given in Kelvin, 273. So we plug these values into our calculator and we find that the number of molecules remaining inside our container is 2.65 × 10⁸ molecules.